Hello everyone. I hope the audio and video both are clear to everyone. So in today's class, we will study the question in your test exam. So we will be starting with the topic of the fluid kinematics. Hello Harjot. So starting with the first question, it says that for two-dimensional flow, the velocity vector has been given as the mentioned in the question. We need to check the properties of the flow. Now the velocity vector is equal to x plus 2y plus 2 I cap plus 4 minus y j cap. Now this is known as the component of the velocity vector along the x-axis, while this is the component of the velocity vector along the y-axis. And this is known as the small v, not y. These are the two components of the velocity vector. Now for the compressibility or the incompressibility, we need to check the of del u by del x plus del v by del y. If this comes out to be zero, then the flow is said to be incompressible. Now we will check whether the del u by del x and the del v by del y, the summation of these two is equal to 0 or not. So if we differentiate the u component of the velocity vector with respect to the x, then we will get the value as 1, because only x will be differentiated, y term will be 0, and a constant will also be differentiated to 0. Similarly, del v by del y, when we will do this, we will get the value as -1. Now from this, 1 plus -1, that is the del u by del x, and it results in the 0. That means the flow is incompressible. It is clear. That means option A and option B, they can be eliminated directly. Now to check whether the flow is rotational or irrotational, we need to check the angular velocity. Now the angular velocity, when we are having only two, because when this x and y component are given, so let's say this is the x direction and this is the y direction. So obviously this plane will try to rotate about the axis which is out of the plane. That means the angular velocity will be obtained along the z direction. And the formula for that is given by 1 by 2 del v by del x minus del u by del y. Now from here, 1 by 2, now del v by del x. If we differentiate the second term with respect to x, then we will get the term as 0 minus del u by del y. If we differentiate the first term with respect to y, then we will get this value as 2. Now from here, it is clear that this will result in the omega z value of -1. That means omega z is not equal to 0. And if this omega z or the angular velocity is not equal to 0, then the flow is said to be rotational. Or it may be said that it is not irrotational. That means the option D will be correct one for the given problem. So all of those who have marked the option D, this will be the correct answer. Moving on to the next question, that is a fluid flow is represented by velocity field. That means a velocity vector is given as ax I cap. Now this is a into x, not a substitution. A x in not in suffix. Ax I cap plus ay j cap. Now we need to find out the equation of streamline passing through a point 1, 2. Now from the velocity vector that we are having, this u will be equal to a into x, and the v component of the velocity vector will be a into y. Now the equation of streamline that can be written down as dx by u is equal to dz by w. Now this is the equation of streamline for 3-dimensional flow. If the flow is 2-dimensional, as in the case in the given problem, because here we are having only 2 components, then we will be considering only this portion of the equation of streamline. Therefore, equation of streamline, it can be written as dx divided by u. It will be a into x. It will be equal to dy a into y. Here a will be cancelled out, and if we integrate the remainder of the term, then the 1 upon x, the integration of the 1 upon x value, this will be natural log of x, that will be equal to natural log of y, plus a constant will be present because of the integration, and let's say we are denoting that by c value. Now here this ln x will be equal to, when the two terms are addition, then therefore the value of x can be written as y into c. Now since we need to calculate the value at certain point, so at point, let's say we are denoting this point by p, which is having a coordinate of 1 and 2. So by putting the values of x and y in this equation, this will be yielding the value of the coefficient, that is 1 by 2. Therefore, if we place the value of this x and y and c in the equation, this is equal to y by 2, and it can be further solved as 2x minus y is equal to 0. That means option C would be the correct one. Moving on to the next question. It says the velocity components in x and y directions of a two-dimensional flow are u and v respectively. That means this is our x direction of the flow and this is the y direction of the flow. In this, the velocity is having a component as u. Now the continuity equation. Continuity equation can be written as del u by del x plus del v by del y plus del w by del z. That should be equal to 0. Now this is valid for a three-dimensional flow, but in this case the question is asking that it is a two-dimensional potential flow. That means we will be taking only the two-dimensional flow, therefore that must be equal to 0. And from here, if we calculate the value of del u by del x, this comes out to be minus del v by del y. That means option D would be the correct one. Moving on to the next question, that is question number 4. A leaf is caught in a whirlpool. At a given instant, the leaf is at a distance of 120 meters from the center of the whirlpool. So let's say this is the whirlpool that I'm trying to draw here. This is the center of the whirlpool, and at a given instant, the leaf is present, let's say, at this position. The whirlpool can be described by the following, that is the radial direction, the velocity in the radial direction. That is given by 60 into 10 raised to the power minus 3 meter per second, while the angular velocity that is given by 300 into 10 raised to the power minus 3 meter per second. Where r is the distance from the center of the whirlpool. Now it is asking that what will be the distance of the leaf from the center when it has moved through half a revolution. That means this is giving us the value of the theta, that is half of the revolution. Now for the complete revolution, this theta is equal to 360 degrees. Now this 360 degrees in terms of pi can be written as 2 pi. Therefore, this theta can be written as, for the given question, that is half of the revolution, written as pi radians. Now, if we look at the ratio of this radial velocity to the angular velocity, now that comes out to be 60 by 300, that is 1 by 5. Now we know that the radial velocity, this can be written as the differentiation of the radial vector with respect to the time. And similarly, this v theta, that can be written as r into omega, that is the angular velocity. Now this omega can be written as d theta by dt. That is, omega is the angular velocity. That means the rate of change of the angle. Now, from the first relation, we can identify so the this VR by V theta, that is 1 by 5, 1 by 5. So from here, we know that this V theta can be written as 5 times VR is equal to R into d theta by dt. Now from here, if we compare both the parameters, that means one more time replacing the value of this, let me give it to minus 5 times VR, that will be equal to, that is equal to R into d theta by dt. Now this R can be written as dr by dt, and this will be R into d theta by dt. Now by rearranging the terms, we will get this value as dr by r, and this will be d theta divided by 5 with negative sign. Now the variation of this value, now the radial component is varying. The question was saying that at a given instant, the leaf is at a distance of 120 meter from the center of the whirlpool. So we need to calculate that at what distance it will be coming by after the half of the revolution. That means the range in which the leaf will be moving, that will be from 120 meter to an unknown value of r. Similarly, this revolution will be 0 to pi, that is half of the revolution. That means this will be natural log of r from 120 to r value, that will be equal to minus 1 by 5 of theta, varying from 0 to pi. Now from here, if we solve it further, we will get the natural log. The first value is r and the second value is 120. And from here, we will get this relation as minus of pi by 5. And since this is a definite integral, therefore we will not be using a constant value here. That means this r, if we solve it further, this will be r by 120, and this can be written as e to the power minus pi by 5, and this will be equal to 0.5301. And from here, the value of R that we are getting, that comes out to be 64 meter. So that means for the given problem, the option B would be the correct one. That means after half of the revolution, the leaf would come to the 64-meter distance from the center of the whirlpool. Moving on to the next question, that is saying that velocity vector of a flow field that is given by 2xy minus x square j into j cap, the vorticity vector at 111 location. Now for this, we need to calculate the angular velocity, because vorticity vector, that is equal to 2 into angular velocity. Now this vorticity is denoted by this symbol, and the angular velocity is denoted by omega, is calculated by half of, this is I cap, this is j cap, this is k cap, this is del by del x, this is by del y, this is del by del z. Now the component of u, v, and w. This angular velocity, when we are using, this is denoted by this symbol, that is omega. Now here, if we place all the values for the respective parameters, I, j, and k by del y, and this will be del by del z. Now the value of u vector, that is 2xy, for j cap, that is x square j and into 0. Now omega value that we are getting, that is half, first of all, for the I cap. Sorry for the disturbance. So this will be 1 by 2 I cap. This will be del, that is 0, minus x square, and this will be positive here. And minus j, this will be 0, plus k cap, this will be minus 2xz minus of 2x. Now from here, the vorticity is equal to twice of the angular. So that means that will be x square I cap minus of 2xz plus 2xk cap. Therefore, at point 1 comma 1 comma 1, that means the value of x, y, and z, the value of all the three factors will be 1. So replacing the values here, the vorticity vector, that will be I cap minus, it will be 4. 2 plus 2, that is 4. So it will be I cap minus 4k cap. The correct option will be option D for the fifth question. Moving on to the next question, that is a streamline and an equipotential line in a flow field. So whenever we are talking about the streamline, so these are the lines which define the direction of the flow. So they are parallel to each other and they can never intersect each other. These are known as the streamlines. Now, if we talk about the equipotential lines, so these are the lines joining the points of equal head. So across the flow, there will be certain lines which will be having equal flow. And these are known as equipotential lines. That means the lines having equal potential or the equal potential head. The shape this is the shape this is which is formed because of the intersection of the streamline and the equipotential lines. This is known as the flow net. And these two lines are perpendicular to each other. That means the correct option for question number 6 will be option B. Moving on to the next question, that is for an incompressible flow field, that means the velocity vector has been given again, that is v cap. V vector, which one of the following condition must be satisfied? So for this, we need to look at the most basic condition of the continuity equation. And the most basic continuity equation is del rho by del t plus rho. If we can take that common, then it will be del u by del x plus del v by del y plus del w by del z. This will be del w by del z, and the summation of these two terms will be equal to 0. Now for incompressible fluid, this rho is constant, it will be 0, and this can be taken out. If this density of the flowing fluid is constant, then this del rho by del t, that means it will not be varying with time, and that's why it can be taken as equal to 0, and this rho value can be taken out. So for incompressible fluid, it can be written as del u by del x plus del v by del y plus del w by del z as is equal to 0. Now in this case, it can be further written as del by del x I cap del by del y j cap plus one vector, and it can be multiplied with the dot vector, that is u I cap plus vj cap plus wk cap is equal to 0. Now the first term, this is known as the divergence, and this is denoted by the value of del operator, which is a vector, and the second term is representing the velocity vector, that is v vector. So this relation can understood that compressible fluid, this velocity vector must satisfy this condition. Therefore, the correct option for the given problem will be option A. Moving on to the next question, that is question number 8. A flow field which has only convective acceleration is. As we have discussed that in the theory part, this acceleration is made up of two components. That is the convective acceleration and the temporal acceleration. That means either acceleration may be varying with the time, or it may be varying with the space. So when this convective acceleration is written, that is written as v into del v, plus this will be del v by del t, that is the temporal acceleration. This is also known as the local acceleration. Now it is saying in the question that the flow field is having only convective acceleration. That means this is equal to 0. This is the relation which is obtained from the statement of the question. Now that means this acceleration or the velocity is not varying with respect to the time. That means if a property of the fluid is not varying with respect to time, then that type of fluid is known to be steady flow. Then that type of fluid is said to be under the steady flow. That means option B and option D, because these are saying unsteady flow, they can be eliminated directly. Now this delta V, this will be varying with respect to time, with respect to space. This will be varying with space because local acceleration is varying with time, but that is not given. So that means our acceleration is depending or is varying only with respect to the space. And a property when it is varying with respect to space at different section points, then that type of fluid flow is known as the non-uniform flow. That means the correct for question number 8 will be option C. The correct option will be a steady non-uniform flow for the question number 8. Moving on to the next question, that is question number 9. It says that a two-dimensional flow has velocities along the x and y directions given by u is equal to x square t and v is equal to minus 2xyt. So the value of u that is given as x square t and the value of y that is given as minus 2xyt. where t is the time. The equation of streamlines. Now, equation of streamline that we have already discussed, that this is equal to dx by u, that is equal to dy by v is equal to dz by w. That is for three-dimensional flow. Since here we are talking about only x and y direction, that means we are talking about the two-dimensional flow only. Therefore, we will be restricting the streamline equation to two-dimension only. Putting the value of u and v in the equation, we will get this value as dx by x square into t is equal to dy by minus 2xyt. Now this t will be cancelled out and one power of the x will be cancelling out the x value. That means from here we will get this value as dx by x is equal to minus of dy by 2y. Now integrating both sides, we will get this as natural log of x, that will be equal to minus 1 by 2 natural log of y plus natural log of c. That is a constant because it is an indefinite integral. So it can be written as twice of natural log of x minus of natural log of y, plus it will be another constant here. Now this can be written as ln. Now this term will be x square and this can be written as, or let me simplify this. This will be ln x square plus ln y, that is equal to another constant. This will be a constant value. So when the two values are multiplied, then it can be written as ln x square y, that is equal to ln c dash, and from here we will know that this x square y can be written as a constant value. This is the equation of the streamline. So the correct option will be option A. Moving on to the next question, or the last problem of the fluid kinematics. In a two-dimensional velocity field with velocity u and v along x and y directions, respectively, the convective acceleration along the x direction is given by. So the convective acceleration, as we have already discussed, that the acceleration along any direction. And since here we are talking about the x direction, so talking about the ax value, this will be the acceleration because of the convection or the convective acceleration plus the temporal acceleration or the local acceleration. This convective acceleration, or the temporal acceleration, that means the velocity when it will be varying with respect to time, that is written by del v vector by del t. And when we are talking about the convective acceleration, that is written by u del v by del x plus v del v by del y plus w del v by del z and plus this value. This is the first part is the convective acceleration, while the second part is the temporal acceleration. Now for the two-dimensional flow field. This will be 0. For two-dimensional flow, this del V by del Z, this will be is equal to 0. Therefore, convective acceleration for two-dimensional flow, that can be written as U del V by del X plus V del V by del Y. So that means the correct option here will be option A, because this U is basically the vector, the velocity vector, and these U and V are the components along X and Y directions. So the correct option here for the convective acceleration will be option A. Now moving on to the next set of questions, that is for the dynamics of the fluid flow. So starting with the first question. That is, consider steady, incompressible and irrotational flow through a reducer. In horizontal pipe where the diameter is reduced from 20 centimeter to 10 centimeter. The pressure in the 20 centimeter pipe just upstream of the reducer is 150 kPa, and the fluid has a vapor pressure of 50 kPa and a specific weight of 5 kilonewton per cubic meter. Neglecting the frictional effects, the maximum discharge that can pass through the reducer without causing cavitation. Without causing cavitation. So let's first draw the reducer. So the reducer, as it is obvious from the name itself, that the reducer is provided when we are reducing the cross-sectional area from the certain value to a reduced value. Now the diameter at this section is 20 centimeter, and at the another section this is 10 centimeter. This is the first section and this is the second section. The pressure just upstream is 150 kPa, and the fluid pressure at section 2 is 50 kPa, because that is the position to avoid the cavitation. We are assuming that the fluid pressure has fallen down to the vapor pressure only. So first of all, what we'll do, we know from the continuity equation. So from the continuity equation, we know that the A1 V1 is equal to A2 V2. Now this A1 will be the pi by 4 into 20 square. V1 is not known. Then it will be pi by 4 into 10 square into V2. V2 is also not known. Now from here, if we compare these to, this pi by 4 will be cancelled out, and this will be 400, that is the square will 300. So that V1 value. Now, considering the datum to be a horizontal surface, this will be the center line of the tube, and it will be at a constant datum distance. So this is the value of Z1, and at this point, this is the Z2. So Z1 is equal to Z2. Now, from the Bernoulli's equation, we know that this P1 divided by rho g plus V1 square divided by 2g plus Z1, that is equal to P2 by rho g plus V2 square divided by 2g plus Z2. That means the summation of all the energies is constant. The summation of all the energies is constant. Now this Z1 and Z2, because these two are equal, therefore they can be cancelled out. Pressure which is at these two sections, converting this value into Pascal, that will be 115 to 10 raised to the power 3. Now this 5 kilonewton per cubic meter, that is the unit weight. So that is 5 kilonewton per cubic meter, and it can be written as rho into g. So rho into g, it will be 5,000 Newton per cubic meter. So replacing the value of the rho g as 5,000 plus V1 square by 2g, that will be equal to 50 into 10 divided by again 5,000 plus V2 square divided by 2g. Now solving it from here further, we will get this value as the first term will be 30 plus V1 square by 2g. This will be 10. Now replacing the value of V2 as 4V1. This will be 4V1 square divided by 2g. Now that means it will be 30 minus 10, that is 20. That will be 16 V1 square by 2g minus V1 square by 2g. That is 15 V1 square by 2g. From here, V1 will be equal to root 20 into 2g divided by 15. From here, if we calculate this value, that is 20 into 2 into 9.81 divided by 15, that comes out to be 26.16, and taking the square root of that value, that is equal to 5.114 meter per second. Now the question was asking about maximum discharge. So the maximum discharge will be equal to at A1 and into V1. So it will be pi by 4 into 20 square into the value of V1, that is 5.114. So this value comes out to be 0.16 cubic meter per second. So the correct option here will be option B. I hope this is clear to everyone. Moving on to the question number 2. A venturimeter of 20 millimeter throat diameter is used to measure the velocity of water in a horizontal pipe of 40 diameter. If the pressure difference between the pipe and the throat section is found to be 30 kPa, then neglecting frictional losses, the flow velocity is so what is happening in the venturimeter? So diverging length, and after that it will be having the diverging length. So this is the first section, and the second section is at the throat. This is known as the throat of the venturimeter. So a venturimeter of 20 throat, that means the diameter of the throat has been given to us, that is 20 millimeter, while the diameter of the pipe at normal position is 40 millimeter. Now the pressure difference, that is P1 minus P2, that has been given to us as 30 kilopascal. So from here we need to calculate the flow velocity. So considering the center line to be at this position, and the center line is at a constant distance from the datum. This is Z2 and this value is Z1 here. And Z1 is equal to Z2. Now from Bernoulli equation, we know that this P1 by rho G plus V1 square by 2G plus Z1, that is equal to P2 by rho G V2 square divided on this Z1 is equal to Z2, therefore this will be cancelled out. Now from here P1 by P2 into rho G divided by rho G, that is equal to V2 square minus V1 square divided by 2G. Now from here this G will be cancelled out. Now applying the continuity equation between section and 1 and 2, this will be A1 V1 is equal to A2 V2. This will be pi by 4 into 40 square into V1, that will be equal to pi by 4 into 20 square into V2. This V1 comes out to be 4 times of V1. This V2 comes out to be equal to 4 times of V1. So this P1 minus P2, that has been given to us as 30 kilopascal in the question. So it will be 30 into 10 raised to the power 3. Now this rho, our question is saying that the water, the liquid which is flowing through the venturimeter, that is water. So it is having a density of 1000 kg per cubic meter. So it will be 1000, that will be placed here. The value of V2 is 4 times V1, that will be 16 V1 square minus V1 square divided by 2. So it will be 15 V1 square divided by 2, and this 1000 will be cancelled out with this. This will be equal to 30. So from here it will be 15, it will be twice the value, and therefore V1 will be 2 meter per second. The flow velocity is 2 meter per second. And the velocity at the throat of the venturimeter, it will be 4 times the 2 meter per second. That's why it will be 8 meter per second at the throat section. So the correct option for this question will be option D. Moving on to the next question, it says that a pitot static tube having a coefficient of C is equal to 1 is used to measure the airflow with water in the differential manometer and a gauge difference of 75 millimeter. What is the value of the airspeed if the density of the air that has been given to us as 1.16 kg per cubic meter? We have been given that the differential manometer, when we are using the differential manometer, let's say this is the differential manometer, which is also known as the U-tube manometer. So this will be the manometric liquid which is filled with the water. So this is water. Now this difference in the height or the gauge difference that is given as 75 millimeter. Now we need to convert this value into the corresponding height of the air column. Therefore, corresponding height of the air column, because this is 75 mm of water, this is the difference. So the corresponding height of air column that is given by h is equal to, let's say if we are having any value as y, then it will be rho of manometric liquid divided by rho of the standard fluid or the fluid in which we are converting minus 1. Now this y is 75 millimeter, while the rho of manometric liquid here will be 1000. That is the here rho, and that is the manometric liquid is the rho of water, and its mass density is 1000 kg per cubic meter. So it will be 1000 divided by 1.16 minus 1. So from here, if we calculate the value of the h, that comes out to be 64.58 millimeter of air column. Sorry, it will be in meter. So just a minute, let me erase this. So this value, when you will be calculating this using the formula that I placed here, this will be 64.58 meter of the air column. Now, according to the pitot tube calculation, V is given by C into root 2GH, where H is the static head. Now this value of C is 2 into 9.81 into the value of H is 64.58. From here, if we calculate the velocity, that comes out to be 35.6 meter per second. Now this is the speed of air. So that means the correct option for question number 3 will be option C. Moving on to the next question, that is question number 4. Is the difference in pressure head measured by a mercury oil differential manometer for a 20 centimeter difference of the mercury level. That means the same thing has to be done. Let's say this is the differential manometer that we are having. In this is the manometric liquid which is filled here. Now this is mercury which is filled in here. Therefore, the rho of manometric liquid will be the rho of mercury, which is 13,600 kg per cubic meter. That is 13,600 kg per cubic meter. Now the difference in terms of mercury level is 20 centimeter. I've told you that whenever we want to convert, it will be H is equal to Y into rho of the manometric liquid divided by rho minus 1. Now in meter, it will be 0.2 meter into rho of manometric liquid, that is the mercury, it will be 13,600. Now for the oil, the specific gravity is given as 0.8. Now specific gravity is the ratio of the density of the oil to the density of the water. Therefore, the rho of oil will be 0.8 into 1000 because the water is having a density of 1000. So it will be 800 kg per cubic meter. So from here, if we calculate these two values, that is 13,600 divided by 800. This comes out to be 17 minus 1, that is 16 into 2. That is 3.2 meter of oil. So the closest option here that we are having is option C. Such type of question where you are calculating the correct answer, but the exact answer is not matching out, then in those cases, you need to take the closest option because any competitive exam asks for the best possible option. So therefore, we will be marking the option C as the correct one. Now moving on to the next question, that is question number 5. Liquid jet issues from a nozzle inclined at an angle of 60 degrees. Let's say this is the nozzle. This is having an inclination of 60 degree to the horizontal and it is directed upwards. If the velocity of the jet at the nozzle let me change the color first. Now let's say I'm denoting with the green color. This is the velocity of the jet at the nozzle, that is 18 meter per second. What shall approximately be the maximum vertical distance attained by the jet from the point of exit of the nozzle? So this, let's say if we are denoting this as theta, that is the 60 degrees. So this will be having two components. This will be V cos theta and this will be V sin theta. Let's say this is the path of the fluid which is coming out of the nozzle. And this will be the maximum height of the fluid flow here. Now, in this case, applying the Newton's second equation of motion, because the water will be experiencing a gravitational flow or an acceleration due to gravity in the downward direction, while this component of the vertical component of the velocity will be moving the jet in the upward direction. So at any point of time, this will be the height which will be obtained. Let's say that is h. It will be equal to v sine theta, that is the component which is forcing it in the upward direction, minus half of gt square. Now for h to be maximum, we know for any quantity to be maximum, the differentiation of it should be equal to 0. So from here, this will be v sine theta minus g into t, that should be equal to 0, which gives us the value of the t as v sine theta divided by g. Therefore, the maximum height which can be placing the value of the v squared sine squared theta divided by g minus half of g into v square sine squared theta divided by g square. 1 power of g will be cancelled out here. So the maximum value of the height that can be achieved is v squared sine squared theta divided by 2g. Now the velocity is 18 meter per second at the start of the nozzle. Now sine theta, that is sine 60, that value is root 3 by 2 its square into 9.81. Now from here, if we calculate these values, this comes out to be 12.4 meter. That means the correct option will be option B. So moving on to the next question, that is question number 6. How is the velocity coefficient CV and the discharge coefficient and the contraction coefficient of an orifice related? Now, whenever we are comparing the theoretical discharge to the actual discharge, we will be using a coefficient of discharge. So if we multiply the coefficient of discharge and the theoretical discharge, we will get the actual value of the discharge. Similarly, if we are multiplying the theoretical velocity with the coefficient of velocity, we will get the actual velocity. So the actual velocity will be obtained as this formula. And the area at the vena contracta, that is, let's say VC, divided by area at the orifice, that is denoted by the coefficient of contraction. And since we know that the Q can be written as area into velocity, now that means if we want to relate all the parameters, therefore Q actual will be equal to A actual into V actual. Now this will be CD into Q theoretical. This will be CC into this will be Cc into area at the orifice, because actually when we are calculating the area for the orifice meter, then it is calculated at the vena contracta. Similarly, it will be Cv into V theoretical. So Cd into Q theoretical, that will be equal to Cc into Cv, area at the orifice, and into V theoretical, it will again be V theoretical. Therefore, this Q theoretical will be cancelled out, and from here we get the relation as Cd is equal to Cc into Cv. The correct option will be option C. Moving on to the next question, that is question number 7. Now it says that which of the following is not a type of force considered in the Navier-Stokes equation. So whenever we are considering the forces in the fluid flow, then that type of study is known as dynamics of the fluid flow. Now the major forces which are considered are the pressure force, the gravitational force, the viscous force, the turbulent force, the compressibility force, and the surface tension force. And the summation of all the forces must be equal to 0. Now, for the gases, the compressibility force will be there, but since majorly we are studying in the mechanical and the civil engineering about the liquid and the fluids, let me change this. This will be the surface tension force, and this will be your compressibility force. Now, this compressibility force is considered to be 0 or is being neglected, then all the equation, the remaining forces, they are told or are known to be forming the Reynolds equation. And if the surface tension force is also neglected, then that type of force, is known as the Navier-Stokes equation. In Reynolds equation, we also neglect this turbulent force. This Navier-Stokes, in this, the surface tension and the turbulent force, both of them are considered to be 0. And let me change the color again. And these remaining forces, if the viscous force is also neglected, then these two remaining forces, these are said to be forming the Euler's equation. And this is the basis for the derivation of the Bernoulli's equation. This Euler's equation equation or the Euler's equation, which is dominantly known as the Euler's equation, this is dependent upon the conservation of the momentum, while Bernoulli's equation is derived based upon the energy conservation principle. So the correct option here, that which type of force is not considered in the Navier-Stokes equation, is the surface tension force, because in the Navier-Stokes equation the forces which are there are the pressure force, gravity force, and the viscous force. Moving on to the next question, that is question number 8. Find the discharge through a rectangular orifice 2.2 meter wide and 1.3 meter deep. This orifice that is given of 2.2 meter width and of 1.3 meter depth. Water level in the stream is 2.5 meter above the top edge of the orifice. So if we are, let's say, this is the rectangular tank, and this is the orifice that is provided here. Now this is the zoomed out version here. Now this water level is at 2.5 meter above the top edge of the orifice. Therefore, the H1, that is, let's say, the height of the fluid here in the container from the bottom, it will be 2.5 plus 1.3 meter. That will be, let me write it here, this will be H1 and this will be H2. Therefore, H1 will be 2.5 meter plus 1.3 meter, that is the depth of the orifice. So it will be 3.8 meter in total. And H2 will be 2.5 meter. The width of the orifice is 2.2 meter. Now this discharge can be written as Q is equal to 2 by 3 of discharge into H2 to the power 3 by 2 minus H1 to the power 3 by 2. Now if we replace all the values here one by one, so this will be 2 by 3. For the orifice meter, the value of the CD that varies from 0.64 to 0.69. So let's say we are taking an average value of 0.67 into the width is 2.2 into square root of 2 into 9.81. The value of H2 is 3.8, its power 3 by 2 minus 2.5 to the power 3 by 2. Now try to calculate this first, and if we get this value, this will be 3.8 to the power 1.5 minus 2.5 to the power 1.5 . So this value that we are getting, that comes out to be equal to 13.9 cubic meter per second. So considering that this value varies from 0.6 to 0.969, so we are considering the minimum value, that is 0.62. Then we will get the exact value that we are having, that is 13.9 meter per second. So that means the option A would be the correct one for question number 8. Moving on to the next question, that is question number 9. An orifice meter having an orifice of diameter D is fitted in a pipe of diameter D. So this is a pipe of diameter D. When we fit the orifice, what is the actual phenomena here? This is the orifice which is provided here. So this diameter of the orifice, so that is being given to us as small d. Now, because of the flow here, this flow will be in this manner. And this minimum depth or minimum diameter that will be obtained, this contractor having the smallest diameter in the cross section. And since this diameter is not known to us, so to calculate this, what we do, we take the help of the coefficient of contraction, which will be the area of the vena contracta divided by the area of the orifice. If this is the orifice and this section is considered to be 1,1 and this is considered to be section 2,2. So when we are comparing these two, 1 and 2 sections, therefore the coefficient of discharge that we will be getting, that will be CD is equal to C naught, or let me write that as CC, that is the coefficient of contraction, 1 minus A naught, that is the area of the orifice, divided by A1 square divided by 1 minus CC square A naught by A1 square. So from here we are getting that this CD is a function of A naught by A1 area, because that is the only parameter which is varying. Now this A naught will be equal to pi by 4 d square, or this is the area of the orifice, so it will be small d. While the area at section 1,1, it will be having a diameter capital D, it will be this value. That means this CD is a function of small d by capital D. That means the CD small d by capital D. Therefore, the correct option here will be a function of d by d only. The option B would be the correct one here. Moving on to the next question, that is question number 10. That is the last question of the dynamics of the fluid flow. Which one of the following is measured by a rotameter? What is happen in a rotameter? So let me give you a brief idea. So there is a device like this. And this is the direction of the flow. This is the direction of the flow. In this, we are having one float. Now this float is having certain grooving at the bottom. Now what happens when this flow passes through those groovings? We zoom this out. So this will be the groovings in this form. So when the flow will be circulating these groovings, it will be generating a vortex, because of which this float will be moved in the upward direction. And as the float will be moving in the upward direction, the distance moved by this float in the upward direction, this will be calibrated to the discharge of the fluid, the discharge which is coming from the bottom of the rotometer. And in turn, we will be measuring the discharge of the fluids by measuring the distance by which the float is moving. Therefore, rotometer is a device used for the measurement of the discharge of the fluids. That completes the dynamics of the fluid flow. Moving on to the next topic, that is the flow through pipes. The first question is, what are the assumptions made for a fluid flow through a pipe? So whenever we are considering the fluid flow, the assumptions are taken that the viscosity is not considered, because we are not considering any head loss. So the head loss which is there, that is ignored. So the viscosity is taken if we are considering the flow through a pipe. Whenever we are writing the equation of the Bernoulli's, that is P1 by rho g plus V1 square by 2g plus Z1, that will be equal to P2 by rho g plus V2 square by 2g plus Z2. At the another section, there will be a component which will be contributing towards the head loss. Therefore, viscosity is considered, that is to be ignored. That means the assumption that the viscosity is not taken, it is wrong. Then these entities, these are the pressure, or in general, not writing about the pressure, these are the energy per unit volume. That means the volume is not considered, it is also the wrong assumption. It is also the wrong assumption. Then mass is not considered. This rho, that is the density of the water, the density of the material is considered. Hello, I hope the audio is clear now. Hello, I hope the audio is clear now. So we were discussing that what are the assumptions made for a fluid flow through a pipe. Viscosity is not taken, so that we have busted. Volume is not considered, so that it is also abolished. And mass is not considered. And since we are considering the mass density, so that is also not true. That means only component that is considered or assumed, that is fluid inertia, is not taken. That means a fluid is allowed to be fully developed. So that is the assumption that is made for a fluid flow through a pipe. So the correct option here will be option A. Moving on to the next question, that is question number 2. To refrain from the separation in subsonic nozzles, the expansion angle must not be more than. So if the angle that we are providing in the nozzle, if the angle is more than 10 degrees, then there will be drift. If the angle is more than 10 degrees, then there will be drift amidst the nozzle. Among the nozzle only, there will be a drift which will be developed. Therefore, at any angle 10 degree, because therefore at any angle more than 10 degrees, the separation will occur. Therefore, the minimum angle that is required for the separation, that will be 10 degrees, or it may be said that to refrain from the separation, the angle must not be more than 10 degrees. The correct option here would be option A. Moving to question number 3. Where is a water hammer developed? So we need to discuss this water vapor phenomena. So let's say this is a system in which this is a pipe in which the water is flowing. And this is certain valve at the downstream side. Now this device, let's say this is the reservoir which is having the collecting the water. When we are looking at this is the reservoir. This reservoir will be allowing certain amount of water, and there will be some turbines which will be here. Now because of the flow of the water, this turbine will be moving, because of which the electricity will be generated and this will be supplied. The rest of the water that will be collected here, or the water which will be generated, which will be wasted here, this will be further taken or just this will be enough to fluid here, that is known as the penstocks. So when this penstocks is carrying the water, and suddenly if we, this is the reservoir, This is the turbine. Suddenly, if we close off the valve, then what will happen? This water which was moving with certain velocity, it will be having certain backward velocity. And it is generated because of in the load. That means this pipeline will be carried ahead as well, but at the downstream part we are not requiring the enough load. That means if there is reduction in the load on the generator, therefore we will be closing the turbine gates or the valves. Thus what it will do, it will create the backward velocity, because of which the wave will be generated in the backward direction. And this to and fro motion of the fluid in a compacted region, that is known as the water hammer. Therefore, the water hammer will be developing in the penstoke region of the power generation system. Moving on to the next question, that is question number 4. It is saying the frictional resistance for fluids in motion is. So the frictional resistance for fluids in the motion is for different flow, that is the laminar flow and for the turbulent flow. Now, according to the laws of fluid friction, for laminar flow, this frictional resistance, which is denoted by a small f, that is dependent or the function of Rf divided by V. And let's say, just denoting here. For laminar flow, this frictional resistance, let's say we are denoting that by Fr, that is directly proportional to F, while for turbulent flow, this frictional resistance is proportional to the square of the velocity. That is, this is V square and this is V. So that means, as per the given option, question number A will be the best suited for the question option that is given to us. Now the next question, that is question number 5. It says that for a compressible ideal gas, talking about the gases here, mass flow rate. So what is this mass flow rate? We know that the flow rate, that is denoted by discharge, that is Q, that is unit volume per unit time. And this volume can be written as mass per unit density. That can be written in this form. Now here this Q will be M upon T into 1 upon rho. Now this M upon T, this entity, this is as the mass flow rate, and it is denoted by M dot. Now it depends upon parameters such as flow area, pressure, temperature, properties of the gases, and so the another factor on which it is dependent, that is known as the Mach number. because this mass flow rate, this is dependent upon the, or it is dependent upon the velocity, and only the Mach number is there which relates to the velocity. That's why the correct option will be the Mach number. Moving on to the next question, that is question number 6. Coefficient of friction for a laminar flow is. So the head loss is given by FLB square divided by 2GD. Now the F here is known as the friction factor. Which is equal to 4 times of F dash. And F dash is the coefficient of friction. Now for laminar flow, we compare the laminar flow with the help of the Reynolds number. And if the Reynolds number is less than 2000, then the flow is said to be laminar flow. So this friction factor is given by 64 divided by RE. Therefore, F dash will be equal to F divided by 4. And from here, we will get this result as 16 by RE. Because in the question, it has been said the coefficient of friction and not the friction factor. So the correct option here will be option C and not option D. Now this Reynolds number is calculated based upon the rho Vd upon mu. This is the relation to calculate the Reynolds number. Moving on to the next question, that is for a nozzle, the vertical intercept between the energy gradient line and the hydraulic gradient line. Now, when we are talking about the nozzle, the water will be coming out in this direction. Now, there will be a certain line which will be representing the energy gradient line. And this will be at a constant distance from the center line of the stream or the nozzle. Now, this is the constant line, that is the energy gradient line. But along the direction of the flow, what will happen? The head will be varying. Let's say at certain instant, this was H1 and this is H2. Because to this hydraulic gradient line to be constant value, this is the reduction because of the friction, and which is known as the head losses. And H1 will be equal to H2 plus HL. That means head will be continuously decreasing along the flow. And when the head loss will be there continuously, and the head is continuously decreasing, that means the intercept between the energy gradient line and the hydraulic gradient line it is continuously increasing. So the correct option here will be option A. Moving on to the question number 8. Now it says a liquid flows through pipes 1 and 2 with the same flow velocity. If the ratio of their pipe diameters d1 is to d2 is 3 is to 2, what will be the ratio of the head loss in the two pipes? And just now we have discussed that this head loss is given by the FLV square divided by 2GD. Now this is the equation of the head loss in pipes, and this equation was given by a scientist combination, that is Darcy-Weisbach, and this is known as the Darcy-Weisbach equation, that is the head loss through the pipes. Therefore, we can say that this HL or the head loss is dependent upon the diameter of the pipe only. Therefore, the ratio of the head loss in the first to second pipe, it will be D2 divided by D1. Now this is the ratio of 2 by 3, because D1 by D2, that was 3 by 2, therefore D2 by D1, it will be 2 by 3. So the correct option here will be option C. Moving on to the next question, that is question number 9. Hydraulic gradient line takes. Now hydraulic gradient line, how do we draw that? That is obtained by connecting the piezometric heads at various sections. It is obtained by connecting the piezometric head at various sections. Now the piezometric head, what is this piezometric head? This is the addition of P by rho g, that is the pressure energy per unit volume, or the pressure head, plus the data. So the piezometric head is the summation of the pressure energy per unit volume, or that is also known as the pressure head, plus the datum head or the potential energy per unit volume. Therefore, to draw the hydraulic gradient line, what we'll do, let's say this is a pipeline here. So at different position, we will insert the piezometer. So the water which will be present in these piezometers, the level of the water indicating the piezometric head, and the line connecting them, that will be a hydraulic gradient line. Therefore, the correct option here for question number 9 will be option B. Moving on to the next question, that is question number 10. On which of the factors does the coefficient of bend in a pipe depend? Now this coefficient of bend, it depends upon 3 parameters. First of all, the radius of curvature, of the band, that is the first parameter on which this coefficient of bend depends. Then the second one is the diameter of the pipe, and the third one is the angle of the bend. So these are the three factors on which this coefficient of bend, which is used to calculate the losses because of the bend, that is dependent upon these three factors. So here, on which factors does the coefficient of bend depends? So the radius of curvature of the bend and the radius of the curvature of the pipe, that is the diameter of the pipe, and the angle of the bend. So the option D would be the most appropriate here, and therefore the correct answer will be option D. So moving on to the next type of question, that is for the viscous flow. So the first question is Hagen-Poiseuille equation. Which among the following is an assumption of the Hagen-Poiseuille equation? Now this Hagen-Poiseuille equation is used to calculate the pressure loss in the pipe. Now, whenever we are considering the Hagen-Poiseuille equation, it assumes that the flow is laminar. The flow is incompressible. The flow is assumed to be incompressible, and it is assumed to be a Newtonian flow. If we are considering the Newtonian flow, that means it will not be turbulent, it will not be compressible. There is no acceleration in the pipe, no acceleration of the flow in the pipe. That means the flow is uniform. The flow properties are not varying. That means the flow will be therefore the correct assumption for the Hagen-Poiseuille equation is question number 2. That how do we calculate the losses for a larger range of Reynolds number? I've told you that whenever the Reynolds number is less than 2000, then the flow is said to be laminar. If this Reynolds number is varying between 2000 to 4000, then the flow is said to be in a transition zone between laminar to turbulent flow. And if this Reynolds number is greater than 4000, then the flow is said to be in a turbulent region. Now, after this number, the Blasius, the scientist, he gave the equation for the friction factor that is valid up to Reynolds number less than 10 raised to the power 5. And the next equation that was given by Nicorazze, that is valid for Reynolds number greater than 10 raised to the power 5. Now for a larger range of Reynolds number, what we do, we take the help of the chart, that is the Moody's chart. So this Moody's chart is a graph between the friction and the Reynolds number. It gives the various values for different K by D ratios. These are different K by D ratios where K is the wall roughness of the pipe and D is the pipe diameter. So basically, Moody chart is a curve plotted between the friction factor and the Reynolds number depending upon the different K by D ratios, where K is the wall roughness of the pipe and D is the pipe diameter. Moving on to the next question, that is when a fluid is called the laminar. Just now we have discussed that whenever the Reynolds number is less than 2000, the fluid is said to be a laminar flow. Moving on to the next question, that is question number 4. For a fully developed pipe flow, how does the pressure vary along the length of the pipe? Now the pressure variation, that is the delta P, that is given by 32 VL upon GD to the power 5. That means this pressure change is linear, although this is decreasing along the flow, because when the pipe flow will be taking from the region of high pressure to low pressure. So obviously it will be flowing if this will be a negative one. That means delta P should be negative. Therefore, along the direction of the flow, the pressure change should be negative. But we can say that the pressure variation is linear. The correct option will be option A. Moving to the next question, that is the last question of the today's class. That is, a circular pipe of radius 7 centimeter is used for the water flow transmission. This pipe is molded into another pipe with a square cross section, keeping the length same. Ignore the thickness of the pipe. Earlier, the section was the circular. This was the circular section of the pipe. Then this section was converted into the square one. We need to calculate the hydraulic diameter of the molded pipe. Now, one thing is common, that the perimeter of both the pipes, that will remain constant. Now, the perimeter of the circular section, it will be 2 pi r, or it can be pi d. Pi, that is 22 by 7 into d, or directly we have been given the value of the r here. This will be 2 into 22 by 7 into 7, so it will be 44 centimeter. Now for the square, the perimeter will be 4 times the A. If the square is of A, side A, that means the side of square will be 11 centimeter. Now hydraulic diameter for the square shape, that will be, now the hydraulic diameter given by 4 times the area divided by the perimeter. Now from here, the area by the perimeter will be 44. Therefore, the hydraulic diameter, if we denote that by capital D, that will be equal to 11 centimeter. Therefore, the correct option here will be option A. So we will end the today's class. We will wind up here, and the rest of the problems that we will discuss in the subsequent lectures. If you are having any doubt in any of the problems that we have discussed till now, or the problems which appeared in your exam, you can ask your doubt in the comment section below, and we will revert to those doubts in the next class. Thank you.